All right, so today we're going to look at parametric equations. Does that sound familiar to any of you? None of you believe you do it in physics? Yes? No? Maybe? Okay, but they're not called that necessarily. And that's kind of like some of the vector stuff. It wasn't necessarily what you called it, but it was the same sort of thing. So it may be that you haven't done them yet, or you have done them, but you didn't call them that, so you're not sure or whatever. But, okay, so I want to start with this picture here. Does this picture look familiar to something that you did in Algebra 2? Parabolas, right? And this would be like a launch problem, where you did launch or drop problems with quadratics. Remember doing that? Okay. So there's this picture, and I found this so that I wouldn't have to draw something pathetic. And so there's this guy. I think there's a story behind it. He's like a king, and I don't know. He's throwing something at his people, whatever it is. So they look like apples. So like he's going to throw them some apples, right? And I guess there's buckets or something. Maybe it's a game. But so he's going to throw it, right? Now, what does the y-axis represent? The height. What does the x-axis represent? What does it represent? What were you substituting in Algebra 2? Was it the distance? It was time. The picture makes it look like distance, right? And when you drew the pictures, that's what you were kind of thinking about. Like when you visualize throwing something, you're visualizing the height and the distance because that's like physically what's happening in front of you. But as far as this quadratic is concerned and what's happening with this, what the x-axis right here really represents is time. Okay? Does that make sense to you? That's what you were doing. You know, after how many seconds, how high were the apples, or whatever it is. Those are the kinds of things that you're going to do. Well, what the parametric equations are going to allow us to do is actually look at this where the picture makes sense, where the x-axis will now actually be the distance and the y-axis will be the height, or whatever may be appropriate for that problem at that time. It's not necessarily always height and distance, but something to that effect. Okay, where we're going to be able to separate it and look at two different things or two different parameters. That's why they're called parametric equations. So I want to show you a couple of graphs that may or may not look familiar. I just know there was one physics student that said, oh yeah, parametric equations. We did that in physics and I know it. So these may be graphs that you've seen, maybe not yet, I don't know. But something that looks like this when you're doing, I know y'all have done like your mg cosine theta, mg sine theta. Have you graphed any of that at all? Looked at graphs of those for velocity maybe? Or maybe something that looks more like this. Okay? All right, where you're given the initial velocity and an angle, and then to get the horizontal velocity, that's where you use the cosine, and then the vertical, you use the sine. Okay, so that's velocity, and that's not necessarily, you know, these are two different velocities, not a height and a distance, but it's still two different parameters. It's that kind of thing, right? Instead of just always having your input-output type of situation. All right, so let's look at the notes. Like I said, I know they're very wordy, but I felt like this was a pretty good way to explain it. I stole it from somewhere and then kind of rearranged some things. And I wanted you to be able to, if you kind of couldn't wrap your mind around what a parametric equation was, or if you thought you had it and then you got confused, you can go back and read this, and I'll talk you through it so it makes more sense the first time. But so it says algebra is really about relationships. How are things connected? Do they move together or apart, or maybe they're completely independent? Equations that you're used to, okay, what you've done mathematically up till now, you use that input-output because we talk about functions like a lot, right? So if we have x equals 3 and we have the equation y equals x squared, we can substitute in the 3 for x and we get y equals 9. Boom, input-output. Make sense? Okay. So, but is that the only way to see the scenario? I will take your watch just like I will take your phone. But is that the only way to see the scenario? So we can set up y equals x squared. That implies that y only moves because of x, right? That the only reason that y changes is because you substitute in an x, like time or something like that. Okay, but could y just coincidentally equal x squared for some hidden factor changing them both? And that's what we're going to look at today, is that, yeah, we might have a relationship of y equals x squared, but is x really driving y, or is there something else that's changing both of them? All right, so here's an example. For every degree above 70, a store sells x bottles of sunscreen and x squared pints of ice cream. So we could write the algebra relationship like this. Ice cream equals sunscreen squared. Okay, so every sunscreen, we put it in there and we square it. That's how many ice creams we sell. Does that make sense to you? And it's correct, but it's misleading. Because really, does sunscreen, however many sunscreens that get sold, does that really determine how much ice cream gets sold? No, it really doesn't. It's just kind of something that happens. So It implies that sunscreen directly changes the demand for ice cream when it's the hidden variable temperature that changes them both. And in this y equals x squared type of situation, is temperature in there anywhere? It's not, right? So that's why it's a hidden parameter there. So it's much better to write them as two separate equations. So the sunscreen is equal to the temperature minus 70, and the ice cream is equal to temperature minus 70 squared. So we're actually using those parameters there. So the idea is that temperature impacts ice cream and temperature impacts sunscreen clarify the situation, and we lose information by trying to factor away the common temperature, right, by kind of dividing that out. So parametric equations get us closer to the real-world relationship. So we find the connection. We might be able to graph something like this, where here's sunscreen, here's ice cream, and we do get this y equals x squared type of situation. However, you investigate the causes, because that's what you're looking for, is what's causing the things to change, and then you isolate the parameter, and you have two different things that you could graph with the temperature. But we're also going to take this and graph it on one graph a little bit differently. So temperature and ice cream, there's still a quadratic relationship, and then temperature and sunscreen, it's more of a linear relationship. Okay, so to get the idea of how to like separate them out, that's what we're doing. It's a pretty good example, because what you will see from a lot of the examples that we do is that the parameter is time. Here it's temperature. A lot of them are time, and so it's easy to have the misconception that parametric equations involve time, but not always. They can. That's absolutely can be a parameter, but it could be temperature. It could be a lot of different things. The key insight is parameters point to the cause. Okay, parameters point to the cause. That's what the parameters are. Why did we change? Maybe it was time or temperature, or perhaps sunscreen really does make you hungry for ice cream. Who knows? Most algebraic equations lay out a connection like y equals x squared. Parametric equations remind us to look deeper. So don't get stuck in the time physics mindset is what happens a lot. So it's not always time as your x-axis. Okay, we're going to split them apart. You kind of understand the basic idea here. We're going to be able to throw in an extra variable and make our equations look a little bit different here. All right. So parametric equations supply a method of separately describing the x and y coordinates of a point. In parametric equations, the x and y coordinates are each written as a function of a third variable t called the parameter. All right. So even though it's always t, okay, but that doesn't necessarily mean it's time or temperature either. I know that's kind of misleading, but you know, x doesn't always stand for xylophone either, right? I mean, it's just not the way it is. All right, so definition of parametric equations. Let f and g be two functions defined on the interval I. So we get an interval there. The relation of all ordered pairs, f of t, g of t, is called a curve C. We're going to get a curve out of it. So instead of having the y and the x in the same equations, we're separating them out and using t for that third variable. So the equations x equals f of t and y equals g of t for t in I, which is that interval, are called parametric equations for C. So the variable t is the parameter. So if a curve can be defined by a pair of parametric equations, we say that the equations give here's another form of the word. Parameterization. It's your $5 word for the day. Parameterization. Okay, you have a parameter, makes a parametric equation, therefore it's a parametrization. Can't even say it. Just different forms of the word. We all good with that? All right, so let's look at what happens here. So a golfer hits a golf ball. The initial velocity and angle of elevation. Those are the things that we would have to know to create the equations. We're not going to create them today. They're going to be given to us. We're going to look at how to graph them and how to make them into the rectangular form. So it says the following parametric equations describe the path of the ball and make a table of values to represent the path of the curve, then plot the points. All right. So we're usually given an interval. I just realized the interval is missing from that. So the interval is where you get your t-values from. So I'm just going to give you the t-values. We're going to do 0, 1, 2, 3, and 4. Okay. And then we're going to make a table of the values, which should be fairly simple, right? For x of t, this is going to give me 130 times 0, which gives me what? 0. So then when I substitute in the 1, I get 130. When I substitute in the 2, I get 260. 3, I get, what? 390. 4, I get, yeah, 52 with a 0, right? That's a good way to think about it. So then I have to find my y values. So I have to substitute them in here. I'm going to get negative 32 times 0 squared plus 130 times 0. What's that going to give me? 0. So then I have the 1. So I'm not going to try and cram it in there. So negative 32 times t squared, and t is 1. So it's just negative 32 times 1 plus 130 times 1. So what does that give me? 98. So then I'm going to do that negative 32 times 2 squared, which is 4, plus 130 times 2. So what's negative 32 times 4? What? 120. 260. So what's that going to give me? $130. Yeah, you take the 260, subtract 100, you got 160, subtract 20, you got 140, subtract 8, you get 132. All right, so then I've got to do that negative 32. Let's see if I can do it up here. Negative 32 times 3 squared plus 130 times 3. So this gives me negative 32 times 9 plus how much? 390. All right, so negative 32 times 9. What is it? 288. So it's negative 288 plus 390. How much does that give me? 102. And then negative 32 times 4 squared plus 130 times 4. So that's negative 32 times 16 plus, what's that? 520. Those numbers are coming from right there, right? So what's a negative 32 times 16? 512. Good. Negative 512, right? So negative 512 plus 520. So what do I get there? 8. Okay. So there are my x and y values that I got from my parametric equations. I have two equations, an x of t and a y of t, with my new variable t. Unlike other things, when you have made charts and gone to plot the points, all of this stuff doesn't go on the graph. The t-values don't actually get plotted. The t-values give you the x and y values, all right? So since the golfer hit the golf ball, this is kind of like the king that was throwing apples at his people. In the past, for you to look at something like that mathematically, you may have done some stuff different in physics, but up until now in math, all you've looked at is maybe the curve of it, so maybe you looked at the height and time. But now we're going to be able to look at the distance and the height, so that what the graph actually represents the curve way more accurately than it did before, because even though it looked like the curve, it really wasn't. So we need to graph this. And so my x-axis here, this is still the x-axis. My x values go from 0 to 520. So I would say maybe this can be 500 here. Right? We go with that, 500. And then mark it off a little bit. I'm not a huge fan of a bunch of hash marks, but 500, and then that can be 1, 2, 3, 4. So make that one 500. So then my y-axis, how high do you think I need to make that one? What do you think my maximum on my y-axis should be? Just to have something to graph. Like maybe 150? That'd be an easy one to do. Okay. So I can make this 150, which means basically just break that up into thirds. So I have 50, 100, 150. Everybody okay with that? So if this is going to represent the curve of my golf ball, what do you think the x-axis actually represents? Does it represent time? What would it represent? Distance, okay? So it's going to represent distance, good. So this is my distance, which is my x of t. And what is the y-axis going to represent? The height, good. So this is the height, which is my y of t. So we're just going to plot them. My first one is 0, 0. These each represent about 100, so about 130, and then about 98. If you need to actually label your little hash marks, you can. And then I've got 260, it's about right there. 132, about right there. 390, and 102, 528. And then this, even though it looks a lot like what you've been doing with these, remember that your x-axis represented time, not distance. And so what's actually happening here is both of these are displacement, okay? Those are words that you talk about a little bit more in physics, like displacement instead of distance and height. So what this is your horizontal displacement, and this is your vertical displacement. Does that make sense to you? Still displacement, okay? Still a distance thing. We good? Any questions about that? All right, awesome. So let's look at the next one. We're going to make a table of values for the curve C defined by the given pair of parametric equations. We're going to draw the graph and show the orientation. Oh, that's what I forgot on this one. Because these do show the actual path, unlike the other ones, we have to add to that little arrows. Where I start here, the path of my ball actually goes like that. That's the path of the ball itself. Where on your parabolas before, that's not really something that you were getting, but that is giving you the distance and the height. Where here, I can't put my arrow on there. Even though we're envisioning him throwing that stuff like that, because this is time, this isn't really the path of the ball. It's just what we think about, which can be very confusing once you learn how to do it the right way. All right, so we're going to draw the graph and show the orientation and state the domain and range. Okay, we're going to state the domain and range as well. So it tells me the interval. Since it tells me the interval, that's where I get my t-values from, right? And I don't have to have, I can use whole numbers here. I don't have to be fancy. So since I'm going from 0 to 5, 0, 1, 2, 3, 4, and 5. So I want you to substitute those in and come up with your x and y values. While I go check roll. It's just a simple substitution. You don't even have to square things like you did on the last one. Sorry, it's not even a place for me to sit. Do y'all agree with me? Is that what you got? Yeah, it was pretty easy, right? You don't get much easier than that. Also easy to mess up on. Easy stuff, though. All right, so I'm going to plot these points. Still going to go to 1, 2. That type of thing doesn't change. -1, 1. -3, 0. -5, -1. Now, that's all the information that we have, and we only want it on that interval. So when we connect these dots, oh, crap. Can't see my dots there. So when I connect these dots here, then I have to decide the, what does it say? It says show the orientation. So the orientation is like the path of whatever's happening, which may not be a path if we're talking about temperature and sunscreen and that sort of stuff. But you know, wherever t is 0, whether it's time, temperature, whatever it is, that's where we're starting our path or our conditions of whatever it may be. And on this one, it did not give us any idea of what was happening. It wasn't a golfer and a golf ball or anything like that. So at 0 is where we're starting, and we're going to 5 of whatever. So our path is here. It doesn't really have anything to do with the slope of the line, because given different information, we could have had that exact same line segment that we have, but our orientation be the other way. Okay? So now I have to state the domain and the range, which is not something that I get from t. That is my interval, so it's written like domain and range, but that's not my domain and range, so I need those. So I want you to think about what the domain and range are, come up with those for what we have on our closed interval. Who wants to give me the domain? Anybody? Should be a piece of cake. -9 to what? To 1. Right? And my range is what? Good. -3 to 2. So algebra 1, piece of cake, domain and range. You just have to apply it to here. Not something that you can get by necessarily looking at this without having your table and your situation that you're having. All right? Any questions? We good? All right. And notice on here, both of these equations were linear, and look what you got here. You got a linear. Where on the last one, you had one linear and one quadratic, and you ended up with a quadratic. All right, so here we're going to make a table of values. We're going to draw the graph and describe the curve C defined by these two parametric equations. Then we're going to write the rectangular equation. So we're going to do the parametric stuff first. Then we're going to look at how to change the parametric into a rectangular. Okay, so how do I know what to use for t? The interval. Good. So it gives me the interval right here. So 0, 1, 2, 3. Okay. So again, I want you to take those, substitute them in, and come up with your x and y values. Do some jumping jacks. Jumping jacks. Once you've got your table, you can go ahead and start plotting them. I'll put my table up there, make sure we agree. We should. Those should be a piece of cake for you to come up with. Do y'all agree with my table? We're all on the same page here? Okay, good. All right, so let's go ahead and plot those points. Once you plot them, does it look like you're going to have a linear relationship again? No. You can tell that there's a curve, right? And we don't connect the dots and make it jagged either. So, that's the best I can do on the board. That's what we should get for our curve, right? So we're supposed to make the table. We did that. Draw the graph and describe the curve. So what does the curve look like? It is half of a parabola. Okay, y'all agree with that? Okay, I like that. But can you really have half of a parabola? I want you to think about that. Does a parabola ever end? No. So it goes on for infinity. Can you take half of infinity? Do you know what half of infinity is? Infinity. Do you know what infinity times 2 is? Infinity. Do you know what infinity squared is? Infinity, right? Like infinity can really mess with your mind. So I know what you mean by half of a parabola, but we have to fix that just a little bit to actually be accurate. So what could I say instead of that? Because it's not really half. It's actually not even close, right? If it's going to go on for infinity. But again, I know what you mean by that. We only have like half of the picture because normally we put a little arrow on there, but we don't even have an arrow. It's not a full parabola, so yes. So how could you say that instead of with a negative, it's not a this? Tell me what it is. Does that make sense? Does my question make sense? It's not, you don't have to get fancy. It's not difficult. Like once you hear it, you're like, oh yeah, it's very simple. We just can't say half. Yeah, exactly. I know. See, and it makes you laugh because it seems ridiculous. Like your idea of half seem to make so much more sense. But that's all it is. It's part of a parabola, right? It's not all of it, but it is part of it. So this is part of a parabola. That's good. Okay, so that's how we described it. Now, I purposely had you graph it before we put it in rectangular form, because when we put it in rectangular form, you should totally be able to recognize that the equation that you get is a parabola. However, what you have here is not all of it, okay, because we have that interval, which is not a domain or range, because those are x and y related, and this is a t parameter thing, so it's all kind of a little different. But what I have here, I can take this and we're going to write it in rectangular form, kind of like how we took polar and put it into rectangular form. We're going to do that with these parametrics. So instead of writing it as x of t, I can just write x equals t minus 1 and y equals t squared. So if I have that, do you see how I could do some substitution here? Okay. Which one, in order to do some substitution, I'd have to solve one of these two for t. Which one you want to solve for t? X. Me too. I wouldn't want to do that one, right? I'm going to do this one. So when we have this and we solve it for t, we get t equals what? X plus 1. Okay? Now that I have that, what am I going to do with this? Substitute. Good. And I'm very bad about always saying plugging it in. The word substitution is way better. I try and catch myself, but I'm going to substitute it. Yes, that's exactly what I'm doing. Right there for t squared. So I get y equals x plus 1 squared. And guess what? I don't even have to square it out. By looking at this, do you know that this is an equation of a parabola? Yes, right? We know that that's an equation of a parabola, and we know that it gets shifted to the left 1, right? Which tells me that this is my vertex of my parabola, because it could have kept going, and maybe the vertex is down here since I don't have all of it. This is the vertex of my parabola. But do you see how this right here doesn't tell me anything about what I have there? I'd have to have this plus my domain and range instead of my parametrics and my interval. It's just kind of a different way of looking at them. Questions about that?
So you can only get this equation without having the graph.
Well, oh, you can. Oh, absolutely. Like, I didn't have to have the graph because I had this. Like, I didn't have to graph it yet. I could have done this. The instructions originally said to take this and make it into rectangular, then make the table, and then decide what it was. Well, when you have this, you already know you're supposed to get a parabola, right? And I wanted you to kind of do that without it. You can, but I can't get this graph by just having this equation. Like here, I had to have these two equations in the interval. To get this out of this, I would have to also have the domain and range. Does that make sense to you? Which is another way of looking at it. So the domain here, we'll do domain and range of this one as well. I don't think it asks for it, but it's okay. My domain goes from -1 to 9, right? No, it doesn't. Oh my gosh. 2, sorry. I'm like looking at the top, giving you half of the range. Okay. 2, yes. Making sure you're paying attention again. Good job. And then my range goes from 0 to 9. And these two intervals here don't match that one there at all, right? Everybody okay with that? I know you don't really know the true why behind it yet, but you need to be able to plot the points and make the equations. And that's it right now, and then we'll look at more of it tomorrow, okay? Any questions at all? Oh, thank you. Yes, we do have to do the little arrows. Thank you. So are my little arrows going, we're going up or down? Is it increasing or decreasing type of thing? Increasing, because my zeros, my t is here, so -1, 0 is where I start, and so yes, thank you, my arrows, dang it.
So if they don't give us the interval, can we just start off with 0 and 2?
Are you not given intervals on these? No, that's a good question. I'm just checking here. They do. Well, but one of them is from -infinity to infinity, right? So what you want to do there is just kind of pick some, and then you don't have to pick an infinite amount because you can't do that, right? But just like here, if you can get the idea of what it is, since it is infinite, at that point could you draw arrows? Does that make sense to you? At that point, I'd have arrows on the ends here where I don't. These arrows don't count. This is just showing you motion. An arrow on the end is different. It's like it keeps going, and that's what's going to happen on that one. And once you plot a few points, by the time you get to number 5, you should kind of have an idea by looking at those two equations you're given, what your graph should look like, so you can kind of have an idea of what to do there. Okay? Does that make sense to you? Any questions? Yes, sir. Yes. All right. And